You can start, Professor.
Okay, hello everybody. So has just disappeared. So first of all, I'd like to thank the organizers of the event for this nice invitation. And I'm going to talk a little bit about nuclear physics as a tool to study and understand neutron stars and gravitational waves. So I will start with this diagram that was proposed by Hertzsprung-Russell, and it shows the luminosity of the stars as a function of the sun luminosity and according to the temperature of the stars. So if you look at this diagram, the blue dots are related to massive stars with high luminosities and high temperatures. Notice that this temperature axis runs differently from usual. So it increases from right to left instead of increasing from left to right. Then if you look at these red dots along this middle line, they are related to the stars that are not as massive and with lower luminosities and lower temperatures. Along this line, these stars are following what is called the main sequence. So that's where the stars spend the longer time in their lives. You can also see above this main sequence line some very tiny dots in blue, and those dots refer to white dwarfs. I'm going to talk about them a little bit later. And then we can ignore these big dots on top that are related to red giants and other kinds of objects that I'm not going to mention in this talk. So why am I showing this main sequence? Because 90% of the time of the life of a star, it's spent in this main sequence. So low mass stars are colder, as you've seen in the graph, and less luminous. And massive stars are hotter, more luminous, and live less time. So low mass stars generally live longer. So how do they live? They live through fusion reaction. So fusion is the reaction that keeps the star alive. If you look at this cartoon, on the bottom left, you can see that there is a kind of fight against the fusion reaction that is exothermic, in the sense that when two nuclei join to form another one, some energy is expelled, as we probably all know, and it's balanced by the gravity of the star. So as far as there is fuel to fuse, this is the mechanism that makes the star alive. However, when the fuel ends, then gravity wins, and there is this strong gravitational collapse. So while the star is alive, it's fusing elements from hydrogen to iron. So this is a kind of onion star. And when you can see all these layers, so those are the chemical elements that can exist or can be formed during the fusion of inside a star. So this also explains why 71% of the elements in the whole universe is hydrogen. So from the beginning, from the Big Bang, when we had just tiny quarks that were that through all known interactions, the four interactions were forming chemical elements. The lightest chemical element is the hydrogen. And then it starts fusing, and we can go up to iron. Why iron? Because if we look at this table, you can see that iron is the one with the highest binding energy. Here we have the binding energy in MeV as a function of the number of particles. So this means that when two nuclei are fusing to form another one, the reaction is favorable energetically, or the reaction produces energy, it's exothermic, until iron. If we want to join two iron nuclei to form another one by fusion, we can still do that. But to do that, we need to add energy. So the energy is endothermic and not exothermic. So that's why we normally say that iron is the last of the chemical elements that is formed inside of these stars. But of course, the others exist, and then we come back to that later. So let's talk a little bit of how the models evolved to try to describe this curve of the binding energy that I have just shown to you. So one of the first models was the liquid drop model, proposed in 1929. And according to this model, the nucleus is like a liquid, which means that it's incompressible, or in other words, the compressibility is limited. And this is so because the internal density of the nucleus is more or less constant. And it presents a well-defined surface. We are going to see a figure. And the radius vary with the number of nucleons, or the radius of the nucleus is proportional to the amount of nucleons, where nucleons are protons and neutrons inside. So this equation shows that radius is R0, it's a constant, around 2 Fermi, times A2 1/3. So the nuclear force saturates, and it's also isospin independent. What does it mean? It means that for the nuclear force, it doesn't matter whether the nucleons are protons or neutrons. It's important for the Coulomb interaction because the protons experience repulsion and the neutrons do not have charge, so they are immune to the electromagnetic interaction. But as far as the nuclear interaction is concerned, they are all nucleons. So this is one characteristic of these guys. So in terms of this, we can describe the binding energy, and we can describe the profile of the neutron and proton densities inside the nucleus. In 1935, Bethe and Weizsäcker proposed the semi-empirical mass formula. Actually, what it says is that if we join Z protons plus N neutrons and look at the mass, this is larger than the mass of a nucleus formed by Z protons and neutrons, because some of the mass is transformed into binding energy. So this expression says that the mass of the nucleus is simply the sum of the masses of the constituents, the nucleons, minus the binding energy. And the binding energy is fitted to adjust this curve. So how to adjust it? So there is a prescription, which is quite simple, that says that the binding energy is proportional to A, and then another minus another term proportional to A to the 2/3, and so on. So I will talk about each of these terms. The first one is called the volume term, because as I have just said, if R is R0 times A to 1/3, R to the cubic, 4/3 of pi R to the 3rd is proportional to A. So this is the volume term. Then, of course, R to the 2nd is proportional to I to the 2/3. So the first is known as the volume term, the second is known as the surface interaction. And then there is the third one, which is proportional to Z. Z minus 1 refers to the repulsion, to the electromagnetic repulsion. So this is the Coulomb term. And then there is another term which is proportional to the N minus Z over A, N minus Z squared over A, which is called the symmetry term. So generally, if we look at the chemical elements of the periodic table, the elements that have the same number of neutrons and protons are just a few. Oxygen 16, calcium 40, you can count. Normally, there are more neutrons than protons. So how to transform a symmetric object with the same number of protons and neutrons into an asymmetric object, that's normally how the nuclei are, we also need to use these symmetry energy, or the energy related to symmetric matter. And then there is another correction that comes from pairing, the fact that nuclei tend to pair. And then there is an expression for even, odd, or even odd nuclei. Of course, you see we have AV, AS, AC, AI, and delta, five parameters to adjust a very simple curve. So of course there are many possibilities, and this is one of the possibilities. So it means that there are many different models with different sets of parameters that can adjust the same curve. This is very basic nuclear physics. Let's see how it's going to evolve so that we can explain neutron stars. So this is those are possible evolutions of stars. So in the beginning we have the star that is alive, and that's part of this main sequence. And then we have three different kinds of stars. Light stars, which we call type 1, with masses up to 8 solar masses, and then type 2, more massive stars with masses up to from 8 to 25 solar masses, and then stars of type 3, very massive stars with masses higher than 25 solar masses. So if we focus on type 1, we see that we have this main sequence. All of them start from this main sequence, and then the rest of their life is much faster. And then they start fusing hydrogen into helium, and then the outcome doesn't matter too much, except for the last one. So if we have type 1, then the star will become a white dwarf. This is what's going to happen to the sun, to our star. If there is a type 2 star, then the death will be more spectacular. There will be a supernova explosion, and then the star may become a neutron star. You can forget about this quark star. So this is a pulsar or neutron star. And then if we have an even more massive star, then after the supernova explosion, we are left, the remnant is a black hole. So I'm going to worry mainly about with neutron stars. So let's see about the history of these compact objects. Why compact? Because they are very massive objects. I'm going to show you numbers soon. And they are restricted to a very low region, to a region not too big, to a very small region, like with a radius of something like 10, 11 kilometers. So very compact. So at the end of the 19th century, 1844, Sirius B was first predicted by Bessel, and then it was observed. Soon later, in 1931, Chandrasekhar described the white dwarf as a gas of degenerate electrons. So the observation done by Clark had a kind of theoretical interpretation done by Chandrasekhar. And Chandrasekhar said that this object, and I show you some numbers, should have a maximum mass of 1.44 solar masses, so 1.5 the mass of our sun. Then in 1944, the first double white dwarf system was observed. So it was a binary system. Normally binary systems, the stars keep rounding around each other. So they circulate around each other. And it was believed that binary systems are very convenient for measurements of masses of the compact objects. So they believed with this binary system observation that the white dwarf was as massive as the sun. So an observation that corroborated Chandrasekhar's calculation. And the radius should be around of the order of 18,000 kilometers. But then Landau thought, what if a massive star is even denser than a white dwarf? So if the mass is higher than 1.44 solar mass, then in this case, probably the atomic nuclei would be so compressed towards each other that they would overlap. And the star should be a huge nucleus. This was Landau interpretation. And it's considered the prediction of the neutron star. And then finally, as you see, this is very interesting because this was this interpretation was given even before the neutrons were detected by Chadwick in 1932. Well, in 1934, some compact objects was seen, and one possible explanation was that they were remnants of supernova explosions. And this was done by Barth and Zwick. In 1939, there were some theoretical calculations done by Tolman, Oppenheimer, and Fokoff, and not two different calculations, but they both pointed to the simulation of a kind of fluid, static fluid, that could be describing these objects, these neutron stars, in such a way that if one had an appropriate equation of state, then these equations developed by them would result in macroscopic properties like mass and radius. Then in 1940, Gamow and Chamber, Mário Chamber, the Brazilian physicist, described the Urca process. So this process was described, and they were working in Rio, and they went to the Urca casino, and then they saw that the money was disappearing. People that were playing, betting in this roulette had the money disappearing, and they thought, oh, this is more or less like what happens in neutron stars, where the trapped neutrinos just leave the stars and carry lots of energies away, and so the energy also disappears, and this was named Urca process. And this was very important in the description of the evolution of the stars. Then in 1964, the quarks were described by Gell-Mann and Zweig. And finally, in 1967, the neutron stars were detected by Jocelyn Bell and Tony Hewish, who was her supervisor. Tony Hewish won the Nobel Prize. Jocelyn Bell, who made the detection, did not. So this is a slide that I like very much. It was produced by Francesca Gulminelli and shows this first detection done by Jocelyn Bell, and the nomination they gave to it, LGM1, which is Little Green Man. So they actually believed that there were some extraterrestrial creatures trying to contact us. But neutron stars, more or less as depicted in this cartoon by NASA, it rotates, can be very rapidly or less rapidly, but and it has a quite strong magnetic field. And it's not part in the diagram I've shown you in the beginning, because it cannot be detected in the visible part of the electromagnetic spectrum. So it was detected in the radio frequency. So let's hear what Jocelyn Bell detected. So let's see, I will just stop this. I don't know, something is, my mouse disappeared.
Yes, we cannot see your mouth.
And I cannot stop this, oh my God.
Yes, you can stop the share.
Yes, I'm trying to.
You want me to stop it and then you try again?
Yeah, because something.
Okay, I'm gonna stop your sharing and then you try again, okay?
Okay, thank you.
Maybe? Okay.
Okay. Yeah, now my mouse is back. Okay. So I'll just try to share something for you to listen.
Then you need to share with this okay?
Let's see. Can you see?
Yes.
So let's hope you can listen to what Jocelyn Bell detected.
Yes, we can listen it. We can listen.
Ou outro aqui.
sempre com frequência constante. É isso. Então, percebam? Podemos ver com olhos muito diferentes.
Okay, so I will stop and I will go back to my presentation. Okay, so there is something that's not working. I don't know why. Yes. Yeah, then perhaps you have to interrupt it again. For some reason, when I go to full mode, my mouse disappears. Okay. But anyway, so that you have an idea of scales, we can see here on the left-hand side, the Earth, and then a white dwarf, and then a neutron star. So really a very compact object, very, very dense as compared with the other two. So which are the main manifestations of these objects? So there are two main manifestations. They can be detected as pulsars, so they are powered by rotational energy. And there is a catalog by McHugh where you can go and you can see all detections of pulsars. About 1900 have already been observed in radio frequencies. And then there are those accreting X-ray binaries. So that's these guys that are orbiting around each other, and they are powered by gravitational energy with rotational periods that vary from milliseconds to lots of seconds, 1000 seconds. Generally, they have masses of the order of 1.4 to 2 point something solar masses, and the radius is quite small, around 10 to 13 kilometers. So very, very dense objects. In 2017, there was a telescope called NICER, that stands for an acronym for Neutron Star Interior Composition Explorer, that was launched and has already sent data to Earth, and people have used this data to constrain equation of states that I'm going to show you soon. And then there was this Athena. There is this Athena that's probably going to be launched in 2030, and it stands for Advanced Telescope for High Energy Astrophysics. Okay, so continuing the history of neutron stars, in 1974, Hulse and Taylor were observing this pulsar in PSR 19 something in Arecibo, and it had a very precise period, and they observed that there was some loss of energy, and they predicted, or they proposed that this loss of energy was the first indirect measurement of a gravitational wave. And actually they were awarded a Nobel Prize in 1993, and that's this picture. They are very happy celebrating the Nobel Prize. But finally, in 2015, so more than 100 years after Einstein proposed the existence of the gravitational waves, they were actually detected. And this first detection was due to the two colliding black holes. So they collided, they merged, and they emitted gravitational waves. But I'm concerned about neutron stars. So what I like is this detection that was noticed, that was everybody knew about in 1917. So LIGO and Virgo detected the first gravitational waves produced by two colliding neutron stars now. And this was a fantastic event. Why was it so? So this is the advertisement of the paper that announced it. And then this is very fantastic because this was a multi-messenger event. So it was not only detected through gravitational waves by LIGO and Virgo, but it was also detected, the signals arrived at lots of different detectors around the world through gamma ray, X-ray, ultraviolet, optical, infrared, and radio frequency. So this was the beginning of the era of multi-messenger astronomy. So you see all those telescopes, they could also see the same extraordinary event. That was very nice because this event was localized, and so not only detected, but they could point out to exactly where it had taken place. So what does it have to do with nuclear physics again? So the idea is to go from microscopic physics, so nuclear and quantum physics, to macroscopic properties related to these astronomical observations that have been made. So what do? We start from an equation of state. What's an equation of state? It's something like PV equals nRT, like you learn in chemistry at high school. So we have, of course, much more sophisticated with ingredients that describe nuclear physics. So we start from an equation of state, and then we use this Tolman-Oppenheimer Fokoff equations I mentioned behind that are related to hydrostatic equilibrium. It's a fluid and hydrostatic equilibrium that's described by this equation of state. And as an output of these differential equations, we obtain macroscopic stellar properties. So let's see how it works. So I will start from the simplest case, is a free-form gas at 0 temperature. So if you look at the left, you have the energy density, the pressure, and the density of a degenerate gas. So in terms of so we have this, the filling of the Fermi levels, and then Kf is the Fermi momentum, and then we know that we have this gas, that the degenerate pressure is also related to this, all those simple integrals that can be performed by hand. Okay, once we have this equation of state, we can plug them in as input to this Newtonian equation. So we are not the TOV equations yet. Those are just simple Newtonian equations that give us solutions for the pressure and of the mass of this gas. Notice that I'm always using natural units. I've written H equals C equals 1, but G, the gravitational constant, is also equals to 1. And then once we do this calculation, we obtain something like that. So let's assume first that the mass is the electron mass. And then you have an equation of state graph, which has this form here on the left-hand side. Pressure against energy density, and this can be either in MeV per Fermi cubic, or in Fermi to the -4, or in MeV to the 4th, so depending on how which units we want to use. But I think the more simpler way of seeing energy density is MeV per Fermi cubic. And of course, I didn't put a scale because it depends on the mass of the element that I'm using, but the shape of the curve is more or less the same. So once we have this equation of state, we plug it in this Newtonian equations, and then we obtain this mass radiance plot. This is what Chandrasekhar saw. And then if the mass is the electron mass, we have an electron gas, and then the maximum mass, the top of the curve is 1.44 solar mass. But if we have a neutron gas, can we do the same thing to describe a neutron star? And then we just plug it in, and what we obtain is what we have on the right-hand side bottom, and we see that the maximum mass is 0.7 solar masses. Well, this is not what I had said before. What I told you is that the max, Landau proposed neutron stars, an object that would be more massive than a white dwarf. And the observations also show that a neutron star can have a mass in between 1.4 and 2 solar masses. So, of course, there are things missing. Which are the missing bits? First of all, no nuclear interaction in the equation of state. So this has to be included. And secondly, then the hydrodynamics has to be properly taken into account, so that simple Newtonian expression becomes this expression that you have now with corrections that come from special and general relativity. So if we do that now, if we look at a certain model and use it as input to the TOV equations, I'm going to show you the results. They come much closer to what we want. So first of all, let's choose an appropriate equation of state. So the existing models, they're all parameter dependent. You remember the liquid drop gas equation or the Bethe-van-Zwicker mass formula? There are many parameters. So all those parameter dependent nuclear models, they have to describe some nuclear physics, which are the nuclear, we call them nuclear bulk properties, and they are saturation density, binding energy, symmetry energy, and also its derivatives, and incompressibility. So this is the minimum that has to be satisfied so that we can trust an equation of states. So of course, if my expression has many parameters, I can have many different models, and they can be either non-relativistic, which means that they can be used as a solution of the Schrödinger equation only. H psi is equal E psi, where H there is the potential, and the potential is a potential like with Saxon, a potential that reproduces nuclear physics knowledge. But it can also be relativistic, and then instead of solving Schrödinger equation for the nucleons, we would have to solve Dirac equations. So how do we choose? So this is a graph that shows the binding energy as a function of the density, and you see that the minimum is going to give us the incompressibility. That's one of the characteristics of the nucleus, as I told you before. So there are many curves here, you don't have to worry about them, but my point is that different models can still explain reasonably well one point, that's the pointing of the saturation, that's the minimum of this curve, but can be different, very different models if we move towards higher or lower densities. And then there is another ingredient, which is very important, that's the symmetry energy. How do we define this quantity? So the energy of the system in terms of its density, baryonic density, and its asymmetry, which I'm going to call delta, is proportional to the energy of a symmetric system plus the symmetry energy times this delta squared. So this symmetry energy is simply the second derivative of the energy density with respect to the asymmetry taken at zero asymmetry, where asymmetry is the difference between the densities of neutrons and protons. So if the system is symmetric, the density of neutrons is equal to the density of protons, and delta is equal to 0, which means that I have a proton fraction equals to 1/2. It means half of it is protons, is related to protons, and half of it is related to neutrons. If I try to put it in terms of a graph, a figure, you can look at this figure of the binding energy with respect to ρ. This is very flat because of the scale I've chosen. And then you see that you have this binding energy for symmetric nuclear matter, which means delta is equal to 0, equal number of protons and neutrons. And then we have just neutron matter. So the symmetry energy is at a fixed density, at the saturation density, around 0.148 to 1.17, depending on the model. I fix this saturation density and I look at the difference in energy. And this difference is what we call the symmetry energy. And this is related to what I've told you in the very beginning when I've shown the Bethe-van-Zwicker mass formula. So this is also an important ingredient and it has to be satisfied. And then if we look again at different models, you see that they all come out at more or less the same point, at the same value, around 0.2. Normally the number we look is 0.12, which is a little bit lower than the saturation density. And then they just go apart, so they can be anything. And then I also have another picture that I've taken from Dr. Jirina Stone, where she analyzed many non-relativistic models, and then your situation become even more bizarre. Some of the energy symmetry even tend to 0 at not too high densities. And why is it important? Because I want to analyze neutron stars, and neutron stars are very dense objects. So the baryonic density is quite high. So there are many constraints that come from experimental data that have to be fulfilled so that an existing model is reliable. I'm not going to enter into details, but some of these constraints are the incompressibility, the symmetry energy, those things that I've just talked to you. It's the slope, that's the slope, it's the derivative of the symmetry energy, and the incompressibility. These numbers can come from experiments, and then we can have constraints. So not too long ago, 240 non-relativistic Kerr models, so non-relativistic models were analyzed, and only 16 were approved. And then 263 relativistic models were tested, and only 35 were approved. So I like to work with relativistic models, and I like to work with relativistic models that can satisfy nuclear matter properties. So I prefer to work with these 35 approved models when they are tested against nuclear physics. So which are the usual steps? So we normally perform a mean field approximation, and then we use Euler-Lagrange equations that give us equations of motion, and then we have the energy tensor equation of states, and finally we compute the energy density, the pressure, and the baryonic density of the system, and then we plug those guys into this Thoma Oppenheimer-Volkoff equations and obtain mass and radius. I'll just skip this 1 second and I'll come back to it, and I'm just going to show you this graph here. So the graphs on the left give you the mass in terms of the radius. This is what comes out from the TOV equations, okay? And when I want is, you see, I've just, I had shown a sketch before for a free Fermi gas, and those are real, more realistic results that come from equations of state that really describe nuclear physics with nuclear interaction. Then you see that the mass, the maximal mass really come closer to 2, or at least they are all much higher than 1.4. That's what we expected. Okay, so I'll go back here. I have read. Okay, so another important constraint then comes from this incredible event that was the gravitational wave that detected in 2017, and then we have here what happens to this binary system. So the neutron stars are orbiting around each other, and then they finally merge. When this happens, there is this tidal field that's induced by this quadrupole moment, and we can calculate that. This is called tidal polarizability, and it's given by this expression, 2/3 of K2, K2 is known as the second order Love number, and it comes from calculation in general relativity, and C is the compactness of the star. G is gravitation, is the gravitational constant. R and M are the radius and mass of the neutron star. So what's the moral of the history?
Professor,
Yes.
I'm sorry. You have 10 minutes, okay?
Okay, thank you. And then what's the outcome of this history? It means that we need an equation of state. Okay, so we need good nuclear physics to try to describe these things. So this is something, these first two things I've already told you. So from the 263 nuclear models I tested, I had 35 approved. So I used this 35 and checked how many would satisfy astronomical constraints. That's neutron stars of the order with masses of the order of 2 solar masses, and then I got 15. And how many of them would satisfy this tidal polarizability restrictions that came from this gravitational wave detection, and I obtained 24. But only 5 can describe at the same time massive neutron stars and satisfy gravitational wave constraints. So just to give you an idea of how this is calculated, in a binary system, one of the mass is fixed. I'm going to call it M1, and the other one is obtained from this chirp mass. Chirp is chirp mass, which gives a relation between these masses, and this number is also inferred from the gravitational waves. Once I have these two neutron star masses, I can look at the solution of my TOV and obtain the corresponding tidal polarizabilities. And this is what I've already told you, and those are the results. So again, we have here the mass radius results on the left-hand side. And then if you look at the bottom, we have this λ1, λ2 results from the two objects, 2 neutron stars in this binary system. And we would like to have equations of states lying within these confidence lines. So there are these wavy lines that represent 50% and 90% confidence rate. So we know that the results are, we can trust if the equations of states lie within these two lines. And then we can see that most of them do, although many of them do not satisfy very high neutron stars. But look that recently there is an indication that some stars can have even higher mass, some neutron stars. They can reach 2.2 solar mass. And then we have to, if you look at my graphs here, just some of them go over these 2 solar masses. Then we have to go back and revisit our equation of states. So this is the structure of neutron star. This is this graph was, this picture was drawn by Danny Page, who is a famous physicist who works with this area in Mexico. And then you see that you have this core, and then there is this crust. And this crust has an outer crust and an inner crust. And in this inner crust, we believe that there is a phase that we call pasta phase. And it's called pasta phase because somebody was very hungry when looked at this structure, and this is a frustrated system. And I'm going to skip this altogether. I'm going just to show you that if this situation is possible, if this pasta phase really exists, I'll go back to this graph here, you see that it lies in between these 2 stars in the equation of state. So if you look if you look to the left-hand side top, you see that there we have a graph for this equation of state, energy density in terms of the pressure. And you see that before the first cross, we have what we call outer crust. In between the 2 crosses, we have this pasta phase. And then for higher pressures and densities, we have the inner core. So how important is the pasta phase? If we analyze, then we have computed the Love number, and we have computed this tidal polarizability, and we have seen that at least for this gravitational wave constraints, the pasta phase is not terribly important. So although if you look at K2, let's look at 2 red curves, for instance, they are like different, or 2 black curves, they are different if we have, or we do not have included the pasta phase. But if we look at the polarizability, we have that these 2 curves lie very close together, so it's really not very important. So I'll skip this and this and this, and then I'll go back to some recent LIGO detection. That was the merging of 2 objects. One with 23 solar masses, so it was clearly a black hole. And another one with 2.6 solar masses. So the most massive neutron star detected or inferred so far had a mass lower than 2.5 solar mass. And the least massive black hole had a mass of the order of 5 solar masses. So this object recently detected is in what is normally called as the mass gap, in between 2.5 and 5 solar mass. What is it? Is it a neutron star or is it a black hole? If it is a black hole, well, no problem with our theories. But if it is a neutron star, then we have to revisit this equation of states, because you saw in the previous slides that they do not reach 2.6 solar mass. They can hardly reach 2 solar masses, 2.1, but 2.6 is way above. And then perhaps we have to revisit this Tolman-Oppenheimer-Folkoff equations that was for a perfect fluid. And one way of doing that is using modified gravity. So I have here a figure. If you look at this purple curve in the middle, this is the solution of the TOV equation. And then we have lots of different curves that were obtained with different parameters of this Rastal rainbow modified gravity. So I've used another theory, and then we can actually accommodate a much higher neutron star. And also with something I didn't talk here, but this gravitational wave also gave restrictions to the size of the radius. So the radius of the neutron star is not expected to be 13 kilometers. This is a little bit too high. It's really expected to be around 11 kilometers. So 1.4 is something that you can see in the middle of this curve. You can, if you look at it, you see that the maximum mass always has a radius which is, no, I'll rephrase it. I'll go back here and I'll show you. Yes, if we look here, the maximum mass has a radius that is normally lower than the 1.4 mass, because the 1.4, the radius, the curve does like this, the radius is larger. But if we use modified gravity, then we can obtain a different behavior overall. We can have a 1.4 star, which is called canonical star, with a radius which is smaller than the maximum star mass, the maximum star mass radius. So maybe this is something we can also use. I haven't talked about the hyperons, but the hyperon, there is something called the hyperon puzzle. When we include hyperons in our equation of states, and they're expected to be there due to this Fermi mechanism of filling out these gas levels, when the hyperons are included, our equation of state becomes softer. What does it mean? It means that it supports lower pressure and hence gives a lower maximum mass. So if we do incorporate hyperons in our equation of state, then we can, it's more difficult to obtain two solar mass stars. But with the modified gravity, we can do that. So just to finish, this is the QCD phase diagram, and I'm going to, I want to show you the neutron star region. So you can see that we have these compact star regions, we have these proto-neutron stars and quark stars. So the density is very high. This is around from 6 to 10 times nuclear saturation density, and nuclei are here around 1. So you can compare the densities which are involved. So those are really very dense objects. And then if you want to learn more about neutron stars, I have I coordinate a channel that's called Women in Science. And there is one video number 49 with something like, they are always short videos. So this one has 3 minutes only. You can go and watch it. And then there is a very nice description of neutron stars based on just cartoons. Even an interesting child could understand a bit, I guess. So you are all invited to visit the channel and to listen to this nice video. And of course, it means that we have lots of work to do, right? Physics and imperial science, I like very much this sentence. It's not physics unless it can be tested empirically. So that's why nuclear physics constraints are very important. If we want an equation of state, it has to reproduce nuclear physics properties. And it's not proved unless it's verified experimentally. So once I have a model that I think it's okay, I have to go through observations. In this case, it's not experimentally, it's observationally, because I'm talking about neutron stars. But if I want to prove that the model is correct, it has to verify something that I can detect. And then I will finish with these sentences to remind you that nuclear physics is really very important. Out of the 4 interactions we know, gravitational, electromagnetic, nuclear, strong nuclear interaction and weak nuclear interaction, 2 of them are nuclear interactions. So this is indeed important. And you can look there, and it says, in the sentence says, when you look up at the night sky, remember that almost everything we see is the result of a nuclear reaction. So that's what I was trying to tell you, that when the star is alive, it's alive because of nuclear fusion. So it's a nuclear reaction. When it dies, if it's one of the corpses or one of the remnants is a neutron star, and it can also be explained through nuclear physics. And one last sentence before I finish. We are made of star stuff because of these chemical elements I've shown you, that they are synthesized when fusion is taking place, but the other elements with a higher atomic nuclei, they can be synthesized in the universe in different ways. One of the way is through the supernova explosion, and another possibility is the merging of these black holes and neutron stars objects. We do have the conditions necessary to obtain heavier chemical elements. So that's it. Thank you for the invitation. And I think, Isabella, you have to interrupt the sharing of my talk.
Okay. Thank you very much, Professor. It was a great talk. I've learned a lot with it. And now we are going to go for the questions. But before, I want to remember the students that are going to present today, the short talks in the poster section. Please stay in the room a little bit at lunch, okay? So now for the questions, we have one in the chat. Rodrigo, you want to speak up and speak up for a question, or I can read it? If you want, you can turn on your mic. You can read it. Okay.
If you want to speak Portuguese, there is no problem. I understand Portuguese now.
Of course. Okay, so I'm gonna read it. I've read it that neutron stars are very smooth objects and that the mountains on their surface are in the order of centimeters. When two neutron stars merge, is the resulting neutron stars just as smooth?
I don't know. I don't know anything about it, so I cannot answer your question.
Okay. Is there
That's very
another
interesting,
question?
though. This is very interesting. I'm going to check and I'm going to see what happens, what kind of, from where we can have this kind of information. You see, this is very interesting because this is an object of 10 kilometers. And then they were telling me that within 10 kilometers, somebody has precision to the term a mountain with centimeters. So maybe those are just bumps in the crust. I don't know. I will try to find out what this means. Okay, Carlos, you can speak.
Carlos, you can open your mic, or you want me to open it?
Opa.
Okay.
Can you hear me, guys?
Yes.
Okay, thank you very much. Hey, everyone. So I have a question, actually. So at some moment of your presentation, you show some picture of neutron stars, and there are some magnetic fields there. And a curiosity came to my mind. And as far as I know, people don't know the origin of this magnetic field. Do you know any progress about this origin of this magnetic field?
No, this is something that can be computed depending on the internal composition of the neutron star. But everything is just very academic because the magnetic fields, there are two types of neutron stars actually. The ones I've told you about, those are they are generally called pulsars. And the magnetic field at the surface of this object is of the order of 10 to the 12 Gauss. There are another class of objects, something like 20, 30 have been detected. Not many have been detected, but they are called magnetars. And these magnetars have a much stronger magnetic field at the surface of the order of 10 to the 15 Gauss, 3 orders of magnitude higher. And actually, how to compute these strong magnetic fields is, or where do they come from, is still an open question. But we can have equation of states that describe reasonably well what happens to the magnetic field inside of these stars. So although we cannot, this is very common in physics, you see. Sometimes the question why is it's more difficult to answer than how. So it's very common that we can explain how something works, but we cannot say why it is working that way. This is a common question in many different fields in science, actually. So concerning magnetars, we already have many answers. Even magnetars that with magnetic field is stronger than normal pulsars. We can already describe many things, but we do not know how to explain why these things formed and what's the mechanism behind it. But there are also simulations, so there is ongoing work towards this direction.
Thank you very much.
Yes, that's true. The spin of the neutrons, or the spin, not only neutrons, you see, inside somebody, I've just reading something that's written here, and I opened the chat. That, of course, the spin of these objects are responsible for the production of this magnetic field, but there is something else. It's not enough to compute these high magnetic fields.
Just a comment. I also heard about some ferromagnetic phase. Did you hear about it? Something?
This is called CFL, color flavor locket phase. Is that what you're talking about?
I don't know. I'm not. I heard about some ferromagnetic phase. I don't know what's about.
Yeah, no. Yeah. I don't know. What we can do is that we can look at the QCD phase diagram, and we can see how it changes if we include magnetic field in. You see, the QCD phase diagram shows you hadronic matter and gluon plasma. It would be a different QCD phase diagram if we had strong magnetic fields involved. And of course, it would have consequences in everything that's described by the all the regions that we try to describe, including neutron stars.
Okay, so we are going to have more 3 questions. Gabriel has something on his chat, please.
So Roger França is asking which are the conditions on the supernovas that lead some stars to neutron stars, some stars to black holes, and also he would like you to talk a little bit more on brown dwarfs.
Well, I cannot talk much about brown dwarfs. I'm sorry, there is something going on here. The conditions of after we have the supernova explosion, there are different kinds of supernovas. So depending on the massive star that gave rise to this supernova explosion, the outcome is going to be very different. So this is also the result of simulation in the evolution of neutron stars. So those are simulations. And the simulations depend on lots of thermodynamic quantities. And depending on these thermodynamic quantities, plus the equation of state which is used, plus the mass of the stars involved, lots of these things lead to different scenarios. That's one of the pictures I tried to show you. One of the scenarios says that the remnant is a neutron star. And sometimes this neutron star can still become a black hole. And the other scenario is that it goes directly to a black hole. But those things are results of simulations that I don't do. So what I know is that things that I read to understand neutron stars. Okay, Landau's interpretation of a neutron star. I can show you. Okay, so first I'll talk about Landau's interpretation of a neutron star. If you look at Landau's paper, he does not say that it is a neutron star. He does not use this expression. What he says is that if maybe I'll go back to my slides. Let's see. Just 1 second. Okay. Okay, so this is a free Fermi gas, okay? And both Chandrasekhar and Landau's calculations were based on these things. And then you look that this depends on the mass. So if this is the mass of the electron, then I would have a white dwarf, and the results are very nice. But if the mass would be as high, you see, the mass of an electron is 1/2 MeV, 0.511 MeV. And the mass of a neutron is 1,938 MeV. So it's the difference if I compute this from an electron or if I compute it for a neutron star is that when I go back to this equation here, the scales are very different. And the fact that the scales here are very different, or whereas the curve is more or less the same, gives rise to very different mass radius relation. So this actually here is not one star. This is a family of stars. So for each point, we have one star with its respective radius. So for the white dwarf, everything is fine. But for the neutron star, it's not fine. Because what Landau said was, okay, so let's assume now that instead of an object with 1.44 solar mass, we could detect an object with 1.5 solar mass. You see, just a little bit more massive. Then this result could not be solved. And then what he said, and that's very nice, because if you look at the video I've told you that's in my channel about these cartoons, it shows how you compress matter and how this hadronic structure of 3 quarks inside gets closer and closer and closer, and it's as if we have this huge amount of protons and neutrons inside. And then, of course, there is something I didn't tell you about, but to have any stable neutron star, you need other conditions. You need beta equilibrium, which means that you have the weak nuclear interaction has to be present, and you also need charge neutrality. So if we have a weak interaction, it means that instead of neutrons, we must have at least protons and electrons. And then if we have protons and electrons, as well as neutrons, we have something that tells us that it's still charged neutron. So the amount of electrons has to compensate the amount of protons. And then it can become more and more complicated with the inclusion of hyperons, the inclusion of muons, and so on. And but what Landau said was that this there should be this very compressed matter, and that's what we now see and interpret as a neutron star. So as far as the graph is concerned, I'll show you this graph here. And then you see that you have this family of stars. So what was the question again? Can you read the question for me? Because then I cannot...
Can I speak up?
Yes. So, okay.
Okay, no, the question was because it more or less peaks at around 2, but it goes down before, and it seems to me that in like the rough sketch, it didn't do, or we didn't see this behavior.
Okay, so this is the peak, this is the maximum mass. If you look at the side of this is unstable. If we calculate this, we see that this region is unstable. So the peak gives the last stable star. That's the maximum one. So the other ones, so we do not have, for instance, 2 stars with the same mass and 2 different radius, because this one is not there. Okay, and then it comes down. This is the result of the constitution of the neutron star that we know. You can also see some results in the literature that does like this, comes like this. Those are quark stars, and then I didn't talk about them here. But this is another possibility, an open possibility that says that perhaps the neutron stars are actually composed by degenerate quarks. And this is because if we come here, you see that the neutron stars are here. So they can be either hadronic stars, so they are here, or they can be quark stars and be here composed of deconfined stars, or they can be hybrid stars. If they are quark stars, then the shape of this mass radius diagram is different. And this is because the star is not maintained by the gravitational force, but it's maintained by the nuclear force itself. But this is another talk for another day.
Thank you very much for the answer.
Okay, so we have a last question, but before, I really wanted to ask for all the people that are going to present today, please stay in the room just a little bit more. We're going to, for the last question, then we're gonna try the share screen and the audio, please. So, Romário, okay, I'm gonna go for Portuguese. Obrigado pela palestra. Como podemos justificar o fato da estrela de nêutrons serem impedidas de virarem um buraco negro pelo princípio de exclusão de Paulo? Pode responder em português.
É assim, ó, o mecanismo que faz a estrela de nêutrons se transformar num buraco negro é um mecanismo, é uma proposta, e diz o seguinte: se eu pegar uma equação de estado de uma estrela de nêutrons, uma equação de estado de uma estrela de quarks, por exemplo, certo? Essas duas que eu estou falando. Se eu tiver uma mesma massa gravitacional, se eu supuser que a massa gravitacional se eu pegar uma mesma massa bariônica, se eu supuser que a massa bariônica é constante, e aí percebam que tem duas massas envolvidas, né? Tem a massa gravitacional, que eu estava mostrando para vocês, mas tem também uma massa bariônica que tem a ver, a gente tem que levar em conta a energia de ligação da estrela. Se a gente supuser que essa mesma massa bariônica é constante nessas duas estrelas, e a gente calcular a diferença de energia que tem essas duas equações de estado, essa diferença de energia é incrível, que ela é da mesma ordem do que a gente chama de gamma ray burst, que é 10 a 53 erg, se não me engano. Né? Então, esse seria um mecanismo de transformação. Então, eu teria uma massa que passou por um mecanismo, emitiu esse gamma ray burst e se transformou num buraco negro. Quando a gente faz esse tipo de análise, essa transformação de férmions em bósons, ela não é levada em conta nesse tipo de análise, tá? Então, eu sei que tem gente que estuda estrelas bosônicas só e como seria o fato delas serem estados preferenciais com relação às outras, mas eu nunca fiz esse tipo de conta. E eu não acho que os férmions em algum momento se transformam em bósons e deixam de obedecer o princípio de Paulo, né? Isso seria possível do tipo do mecanismo BCS, que é o que a gente tem quando a gente tem emparelhamento de partículas na supercondutividade, né? Os dois elétrons se juntam, se acoplam, e quando a gente tem dois férmions se acoplando, o Clepsy-Gordon dá lá um bóson, mas esse tipo de mecanismo para explicar a evolução estelar, eu, pelo menos, nunca vi.
Okay, so we are going to finish here. Thank you very much for the talk, Professor. It was really great.
Okay, I thank you for the invitation. Have a nice lunch at home.
Yes.
See you.